Welcome to this explainer on how artificial intelligence is rapidly learning to see and, more importantly, reason about our world. I am absolutely thrilled to guide you through this today. For the longest time, AI models were basically trapped in a dark room. They could only understand the world through the text we fed them. But that is fundamentally changing. Today, we're diving into vision language models, and we're going to explore exactly how they are bridging the gap between human-like, multimodal cognition and current AI. Alright, here's our roadmap for today. First, we'll cover the multimodal AI revolution. Second, a showdown between GPT-4V and LLaVA. Third, comparing BLIP and BLIP2. Fourth, the evolution of visual reasoning. Fifth, hallucinations and prompt attacks. And finally, number 6, the future of vision. Let's jump right in.
Section 1. The Multimodal AI Revolution. We're kicking things off by looking at the big picture of how text-only AI is finally stepping out into the visual realm.
So what actually is a vision language model? Essentially, these are AI systems that jointly perceive, reason about, and generate content across both vision and language to understand the physical world. They literally bridge the gap between simple perception and complex logic. We aren't just talking about a basic camera that can draw a box around a face anymore. We're talking about a system that can look at a photo of a messy restaurant menu board, read the prices, understand the weird layout, and then calculate the total cost of your order. It's perceiving the visual data and reasoning through it using language all at the same time.
But here's the catch. It takes a massive amount of brain power to process these images. 95%. Just think about that number for a second. A staggering 95 to 99% of the compute in these models goes purely toward processing visual tokens. That makes efficiency a huge, ongoing challenge. Translating high-resolution images or video into something a language model can actually understand is incredibly heavy work. Early models use fixed-resolution processing, which kind of just destroyed all those fine-grained details, so now researchers are desperately fighting to compress these tokens without losing the critical visual evidence the AI needs to actually think.
That brings us to Section 2, Showdown, GPT-4V versus LLaVA. Let's see how two of the current heavyweights tackle these exact challenges head-to-head.
There is a fascinating architectural divide happening in the industry right now. On one side of the ring, you have OpenAI's GPT-4V. It's a proprietary, massive, transformer-based beast optimized heavily with reinforcement learning. On the other side, you have LLaVA. LLaVA is an open-source model brilliantly pieced together using parts like a CLIP visual encoder and the Vicuna language model built on Llama. And get this, it was trained on an incredibly small data set of just 80,000 images. It really is a classic David versus Goliath scenario.
So, how do they actually stack up on specific tasks? Well, GPT-4V absolutely dominates fine-grained perception. If you ask it to find a tiny, closed umbrella in a heavily crowded photo, or read rotated text, or do complex math OCR, it performs beautifully. LLaVA, honestly, really struggles with fine object detection or understanding rigid spatial layouts, like a Sudoku grid. It'll often hallucinate details. But, and this is a big but, when it comes to conversational instruction following, LLaVA holds its own surprisingly well against the giant, despite its tiny dataset. However, we need a reality check. When we look at the MMU benchmark, which tests college-level expert multidiscipline reasoning, human experts score around 88.6%. GPT-4V, it's staggering behind at 55.7%. That is a glaring 33-point gap. It completely proves that even our very best multimodal models still trail far, far behind human experts. We've made massive leaps for sure, but true, reliable expert-level understanding is very much an unsolved problem.
And for the developers out there, there's another massive catch with the open source route. The commercial usage ambiguity surrounding LLaVA 1.5 is a total headache. You might be thinking, awesome, it's open source. I'm going to go build a startup. Well, hold your horses. Even though Llama 2 and Vicuna 1.5 permit commercial use, LLaVA's original dataset was labeled for non-commercial use only. The underlying scraped image rights remain a huge legal gray area. It just goes to show that open source doesn't always mean simple, risk-free commercial deployment.
Moving right along to Section 3, comparing BLIP and BLIP2. Let's explore another major, highly impactful rivalry within the open source community itself.
This is a head-to-head between the older BLIP model and its successor, which honestly completely re-engineered how vision and language talk to each other. The original BLIP uses standard vision transformers. It's super fast for basic image captioning, but if you need multi-step logic, it falls apart. BLIP2 fixed this in a genius way. It slips a lightweight querying transformer right between a frozen image encoder and a frozen language model. This lets them communicate without requiring the massive, expensive compute usually needed to train the whole system end-to-end. It absolutely excels at complex visual QA.
54 times. That is the magic number here. By shifting to this frozen architecture, BLIP2 achieves state-of-the-art results using 54 times fewer trainable parameters than massive models like Flamingo ADB. By only training that small connecting transformer, BLIP2 became an absolute powerhouse that everyday researchers could actually afford to run. It proved that you don't always need a bigger model. Sometimes you literally just need a smarter architecture.
So how are these architectural leaps changing the game? Section 4, Evolution of Visual Reasoning. To figure out if an AI is actually reasoning and not just throwing darts at a board, we use Visual Question Answering, or VQA. It's a core task where models have to answer natural language questions about an image by integrating perception, reasoning, and outside knowledge. Look, it's super easy for an AI to see a kitchen and just spit out the word refrigerator. It is infinitely harder to look at a cluttered counter and correctly answer, what color is the small mug sitting behind the laptop? That takes localization, spatial reasoning, and real visual grounding.
When tracking this timeline, the sheer speed of evolution is just wild. We are rapidly moving from the foundation era of basic static architectures in 2023 straight through the scaling and preference alignment of 2024. Now heading into 2025, we're looking at the reinforcement learning revolution, where models experience their own aha moments. And by 2026, we're projecting a maturation era where highly efficient sub-1 billion parameter models can orchestrate tools and act as fully autonomous reasoning agents.
To manage this evolution, models now use a multimodal chain of thought process. It's essentially a 4-step playbook. Say you wanted to find a specific price on a giant restaurant receipt. Instead of just wildly guessing in one shot, it talks itself through it. Step 1, summarize the layout of the image. Step 2, logically identify the specific target region. Step 3, extract that visual data. And Step 4, actually compute the logical answer. By grounding every single step in visual evidence, the AI's accuracy absolutely skyrockets without hallucinating.
But, of course, it's not all sunshine and rainbows. Section 5, Hallucinations and Prompt Attacks. Let's look at the very real security vulnerabilities in these new architectures.
This is where things get super ironic. GPT-4V's superior reading ability actually makes it way more vulnerable to hijacking than LLaVA. In a famous test, researchers hid a tiny Team Mercedes watermark inside an image. Because GPT-4V has incredible text recognition, it read the hidden text, totally ignored its original system instructions, and essentially got hijacked. LLaVA completely missed the watermark because its reading skills are weaker, making it accidentally immune. But flip the script, and LLaVA is so heavily weighted toward its language priors that it will strictly adhere to an unsafe text prompt even when its own eyes are showing it something completely different.
So the big takeaway here is that despite all these massive leaps, VLMs still suffer from major structural blind spots. Language priors frequently override clear visual evidence. Embedded text can completely override system instructions. And on dense, cluttered scenes, hallucination rates absolutely spike. These models are fundamentally biased toward language. If a prompt asks a leading question, the model will often just invent a plausible-sounding answer rather than admit it can't see the detail. It literally tells you what it thinks you want to hear based on internet text rather than the visual truth.
Which leads us to our final stop today, Section 6, the future of vision. What does all of this actually mean for the immediate future of multimodal AI?
Well, it all boils down to this one ultimate dilemma. As we move to deploy these seeing, reasoning agents into physical spaces, like medical diagnostic tools, self-driving cars, and autonomous robotics, ensuring their security is no longer optional. It is existential. The progress we've covered today is absolutely breathtaking, no doubt about it. But the gap between an impressive lab demo and bulletproof real-world reliability is still vast. So, I will leave you with this provocative thought. If our absolute most advanced visual AI can still be completely hijacked by a hidden line of text, are we truly ready to let it navigate our physical world? Thank you so much for joining me on this explainer. Keep learning and stay curious.